Welcome to Centripetal Charge Motion. This is the 8th video in the New Electromagnetism V5 series, and New Electromagnetism is the 4th paper in the EtherealMechanics series. This video is EM0408. This video will be published to Patreon members first, and then at a later time exceeding 4 weeks will be made public. So we're going to define what centripetal charge motion is, then we're going to derive centripetal charge effects from New Electromagnetism V5, and then we're going to show you an experimental workup where we're going to discuss the first ever electrogravitic demonstration. So centripetal charge motion is section 4.3 of the New Electromagnetism V5 paper. The PDF is available to Patreon members first according to this release schedule, and will be made available to the public 4th of July 2024. So where does centripetal charge motion occur? Well, if you have a charge on a spinning wheel and that wheel is spinning around, that charge is going to undergo centripetal acceleration. And because that charge is accelerating, it will produce the inertial force effects. Okay, but this application here is trivial. In this case here, you can apply the point forms of the inertial force model, which are available in the the Electrogravity series of papers. In New Electromagnetism V5, we're discussing electrical engineering applications, and typically electrical engineering applications are currents and things flowing in wires. So in wires, you get a centripetal acceleration when you have charge flowing around the bend of a wire. So when this charge changes direction, you're going to have acceleration. And that is going to be essentially a centripetal acceleration. So as the charges are accelerating around the bend of the wire, their centripetal acceleration is going to be converted into an inertial force, which is going to affect target charges somewhere else. Likewise, when you have current changing direction around a loop of wire, you have charges that are centripetally accelerating, and their effects can be turned into inertial effects that will affect charges someplace else. This is a Physics 2 simulation of a square loop of wire. And what we have is a target loop which is positioned over one of the corners of that loop in order to detect the centripetal acceleration of the charges around the corner. There's a new feature in the Physics 2 software called a sensor plane. I'm going to show you that now. The sensor plane is basically a plane of test charges that allow you to see the effects of anything you want to see in new electromagnetism. Matter of fact, you can tell the sensor plane to look at just the inertial force, just look at the Coriolis force, just look at the magnetic force, yada, yada, yada. In this case, we have everything turned on. So this is all the effects of the loop on the charges in the sensor plane. The color coding shows the amplitude of the effect, where white is the hottest, down to black, which is the coldest. The scale is logarithmic. You can see a lot more. And let me do a close-up so you can see the little dots there. These little dots are little golden cones that are pointing in the direction of the force. Now what I'm going to do is I'm going to go to the back side of the sensor plane. Now because the sensor plane is bisecting this wire, when I go to the back side, you're still going to see the wires. Let's go to the back side. Okay, and you can see right over the corner, that's where the maximum effect is of the centripetal acceleration of the charges. Now, there is a mistake in the software, but I think it's a happy mistake, because if the charges are accelerating around the corner, then the centripetal acceleration is in this direction, but the inertial force acting on the charges is going to be in the opposite direction shown by the arrows. This is a sign error. I think I'm going to keep it because ultimately these test charges are positive current, and the actual moving charges in a wire are going to be negative current, negative charges. And so that would be the correct direction for positive charges to react to current moving in a wire. That's a happy accident. This is going to be the right EMF that we're going to see with a real wire. We'll talk about more of that later. Now, in the new magnetism paper, this was for part of New Electromagnetism version 3, which was from 2003, I considered, and this paper can be found here, I considered the bend of a wire, and I tried to consider the centripetal motion. Okay, and now if you go back to this paper and you go through this, okay, I consider all the effect of a complete closed loop. And the effect that I got using the old model of magnetism and everything showed the conclusion that all the effects completely cancel and you wouldn't see anything. Okay, I don't think that's true anymore. We were using an old model of magnetism, which quite possibly could have canceled everything incorrectly. Now, I have not gone back through this paper with a fine-tooth comb to see if it was the obsolete model of magnetism or if I'd made a math error. But ultimately, this is why I've been ignoring this effect for 20 years. And ultimately, I had no simulation software back then. Physics 1 didn't come about until like 2019. Okay, and so I was doing a lot of math, and of course, I could have made a mistake. Okay, and also the Physics 2 model has the new fragmentary wire modeling. It probably wouldn't have mattered because back then I didn't know how to handle the drift velocity, which a couple of years later when I got my master's degree, I completely researched that. So. But I didn't go back to this because I still assumed that everything canceled. So Physics 2 is showing that it doesn't cancel. It's there. Okay, now what we're going to happen next, for those people that don't want to go through this next section, which is full of math, full of really strange derivations, you can switch ahead till we start discussing the experiments again. Look for this picture when you zoom ahead. And we're going to start, that's when we're going to pick back up with the electrogravitic demonstration experiment. Again, this electrogravitic experiment is assuming that I was actually wrong in 2003. I hope I was wrong because this is going to be a cool experiment. Okay, for the rest of you engineers that want to stick through this next part, okay, be prepared to be bored if you don't like math. Now, when I wrote the paper, the New Electromagnetism V5, I pretty much copied what was in the 2003 paper. No sense reinventing the wheel. The derivations are almost the same. And I even copied all the pictures so I didn't have to make a choice on what to name all the variables, whatever. Now, but I got into a problem because this old method, in the paper I fixed it. Okay, I got to the point where I fixed it because the problem with this old derivation is that it does not produce a vector form for centripetal acceleration. It ends up with a scalar, because it's derived from a scalar form. All right, and so I did this in the NEV5 paper just to get it done. And I'm still learning about Vortrix algebra. Okay, but in Vortrix algebra, it's a very simple expression for centripetal acceleration. It's basically your tangential velocity, the velocity divided by the radius of the curvature times the radius of the curvature, and that gives you your centripetal acceleration as a vector. Now, for those people not familiar with Vortrix algebra, the magnitude of this comes out to be the magnitudes of these, which is the magnitude of the velocity squared over the radius squared, times the radius, which is v squared over r, which is the centripetal acceleration magnitude. Now, for Vortrix algebra, the direction kind of works very similar to complex algebra. Okay, you have one vector divided by the other. So basically, it's the direction of this minus the direction of that. That's what you would do with complex numbers. Okay, so you have the direction of v, which is at minus 45 degrees, and the direction of r, which is at plus 45 degrees. So if you take minus 45 degrees and minus plus 45 degrees, you get minus 90 degrees. Squaring it does the same thing as in complex numbers. It doubles it. So now you have minus 180 degrees, or just 180 degrees. Adding 180 degrees to any direction basically inverts it. So you can just put the negative of the direction here. And so that's exactly where the centripetal acceleration will be. It'll be opposite the direction of r. And that's what we're seeing here. So it works out great. So let's restart the derivation. We take our centripetal acceleration expression here, and we take our point-to-fragment conversion identity from section 1.2 of the paper. Ultimately, what we have to end up with here is a charge acceleration term in vector. That's the minimum we need to put into the inertial force model, is a charge acceleration term. First thing we're going to do, though, is we're going to take this point to fragment conversion identity, solve for VSC, and then substitute it into there. That's this here, and we pulled out the scalars. Next, what we want to do is, in order to get this into a charge acceleration, we're going to multiply both sides by DSC. That gets us DSC here. That gives us a singular DSC here. And then we're going to do substitute the DSC with QSPM times DLS. What this term here is, this is the quantity of conduction charges per unit meter of a wire. It's based on the material that makes up the wire and the diameter of the wire. That's covered in the paper. So basically this value gets larger for a larger diameter wire. It gets smaller with a smaller diameter wire. And this is what we're going to end up with right here. Okay, and then we're going to do some more reducing and reducing. Now, this here, we have two forms. This is the general form here. We're going to talk about more of this later. This is the form, basically, if you basically have a circle. I'm carrying this along, but we really don't need this. This is a general form that will work for any arbitrary path of wire where this is specific to a circle right here. So now we're ready to insert this into the inertial force model. This is the inertial force model from the electrogravity paper, which is paper EM03. You can find the paper at my website. I'll show you how to get to that at the end. This is the form shown in natural units. In EtherealMechanics, the natural Newton is square amperes. Legacy unit is kilogram meters per second squared. To convert this to legacy force, you multiply by Km. Km is mu over 4 pi. Some people say, well, mu is the permittivity or permeability, whatever, of free space. No, it is not. It is kilograms divided by natural inertia. Period. And I can have a whole discussion on that. But right now, every time you want to convert natural units to legacy units, all you do is multiply by Km. There are no constants of relation at all in ethereal mechanics. Now let's talk about, and we also represent legacy newtons or legacy units in blue so that when they're printed on the same page, we can tell the difference between natural and legacy units. Charge, distance, and acceleration are all in natural units here. So our terminology, when you insert centripetal charge acceleration into the inertial force model, this results in the centripetal inertial effects, and there's forces and there are VIMs. VIM is a new word for EMF. So inserting that equation into here reduces this. Now, again, we're carrying along the circular version, but this is the general form right here. Okay, this is equation 4.11 in the paper, and this is the effect of a fragment on the source loop onto a target charge somewhere else. This is the fragment to point effect, centripetal inertial force fragment to point. Okay, you have to integrate this over a source loop to find the complete effect on a target. Now, this is not necessarily for a circular loop. This can be any arbitrary loop shape, and sections of the loop that have a curvature are defined by their radius of their curvature here. R here, little r, is the distance from the fragment to the target. And people say, well, what if you have a piece of wire that's straight? Well, then that would have an infinite radius, and that would have no centripetal effects. Again, you have to go around a curve to have centripetal effects. So obviously, when your radius goes to infinity, which would be the radius of a straight wire, you're going to have no centripetal effect. So this is the centripetal effect for any arbitrary wire path that you want to model. And again, this is, and you don't have to have a complete loop. You can say, well, I just want to take this half of the loop and see how that affects the target charge, or I want to see how this part of the loop affects the target charge. You know, whatever you want to do. It doesn't have to be a closed, this isn't classical theory where everything has to be closed loops. Okay, you can see how one part affects another. It's very handy. Now, in version 5.0 of the paper, we had the negative signs on these. That is incorrect. This is corrected here, and it's also corrected in version 5.1 of the paper. Now, again, there is what we talked about before is the direction of our arrows are going in the opposite direction. Part of me is thinking that your QSPM, which is your conduction charges, since if you're discussing electrons here, which are negative, you would have a negative sign for your conduction charges here. And that would solve all the sign issues here. But that's one possibility of handling this. I don't know. This is just an idea I'm throwing out right now. For electrical engineering, we want to look at the effects between wire loops, which would be the fragment-to-fragment effects, also known as the interfragmentary effects. So to convert the fragment-to-point model into a fragment-to-fragment model or an interfragmentary model is very easy. All you have to do is divide both sides by QT and then take the dot product with the direction of the target loop. And that's what we end up here, right here. And because we have two diminishing operators in the numerator here, we need two diminishing operators in the numerator here. Now, other people call those differential operators. And for my field of engineering, that's confusing because we have differential amplifiers. And that gets kind of confusing because in calculus, what you're doing is taking a length of a wire and diminishing its length to 0. So I look at these as diminishing operators. And I do that to keep from confusing it with differential, which has a different term in electrical engineering. So these are diminishing operators. That's the term I'm going to use. And so they need to balance. So in order to compute the complete effect between two wires, you need to integrate over your source wire and integrate path integral over your target wire. So it's a dual path integral. Okay, again, you don't have to do the full thing. You can do whatever part or section you want to whatever part or section you want. But again, if you want to see the voltage on a voltmeter, you got to go completely around your target loop. Okay, and again, that is your EMF. That's the new term for EMF. Now, another useful derivation, which is in the paper, I'm not going to go into because it's a long derivation. Instead of having to actually integrate around the bend of a curve, if you take the equations before and you set the length of the curve to 0, then you can get what we're going to call the junction effects. It's like you got current entering this junction and current exiting this junction. Okay, so all you need for this is junction to fragment. This is centripetal inertial VIM. Junction to fragment. All you need is the direction of the insertion into the junction and the direction of the current exiting the junction. And then the distance from the junction to your target point, yada, yada, yada. That's all you need. And this is used throughout physics too, not only for bends in wire, but when we have a curved wire, we just do it at these little sections here. And this is what we're using as our general purpose. We'll talk more about this next week when we can cover Venturi effects because we've unified these junctions for both centripetal and Venturi effects. Okay, so this is the more general. And again, this had the wrong sign in the version 5.0 paper. Okay, this picture is a picture of the experiment we're going to talk about next weekend. I just needed a pretty picture here for everybody to zoom to so we can continue the discussion. So what we saw in the beginning of this video is a square loop of wire for the source and a square pickup wire orthogonal to that square wire. We're also going to do an experiment with a circular piece of wire because we need to be able to verify that we're using the technique of the junction, because remember, we're using the junction technique for both the square edges or the square corners of loops and also for the circular. So we need to validate both sets of effects. Okay, again, this is the sensor plane on top showing the magnitude of the centripetal effect Then if we zoom in, you can see that the arrows all point inward. Again, we have to deal with the sign here, but we'll talk about that again in a later video. Okay, so when we look at the square loop, where we're looking at the corner effects, this loop here is going to pick up 10.5 microvolts. With a circular one, because the bend isn't as extreme near the wire, we're going to have a less effect. But these are both on the edge of measurability. But to get these effects, okay, we need the smallest piece of wire. We're going to take 30 gauge wires where we start. I'll explain how we got there. And we have to put 100 amps through it. Now, we're not going to keep 100 amps constantly. It's going to be pulsed. But we need 100 amps through 30 gauge wire to pick up these tiny microvolt values. So these loops here are probably going to be 100 turn loops so that this guy can be a full millivolt. So this is the bread and butter of why we need to do qualitative analysis. A lot of people say, oh, just keep running the simulation until you get the answer you're looking for. Yeah, you can do that. But when you actually derive the equation tells you a lot of information. I don't have to run the simulation to know that the current through the source wire, the effect goes up by the square. So obviously we want to maximize the source current as much as possible. And the effect goes down by this would be related to the size of the wire. So in order to make the effect go up, we need the smallest wire possible. Again, this value here is the conduction charge in coulombs per meter of the wire. And this is related to the material that makes up the wire, and it's made up by the diameter or the cross-sectional area of the wire. This is derived in the paper. There'll be a chart out there for people to use. Okay, so we will push the maximum current through the tiniest wire. We have 30 gauge wire in abundance. Now, when I did this is from the paper from 20 years ago. This I said was the drift velocity. Okay, again, one of the reasons why I did not know how to handle this back then, I was kind of grateful that it canceled because I did not know how to handle this back then. But it was only a year later before I started my master's degree, and I researched how to do this tremendously. So this is a clipping from the 20-year-old paper. Okay, so the question is, well, how much current can we pass through a 30 gauge wire? Well, if we go to the Wikipedia and wire ampacity, here's 30 gauge. And over here it says that if we put 86 amps, I hope this isn't an eye chart for some people, then it can handle 86 amps up to 32 milliseconds, which is great. I only need 10 milliseconds to make a measurement, so we could probably go above 86 amps then. Because as you see, as you go down in amperage, the wire will last longer. So it can handle 10 amps for 10 seconds. It can handle 15 amps for 1 second, 86 amps for 32 milliseconds. So I should be able to get to 100 amps easy with this. So what I did is I took that data from that chart and I curve fit it, and I found out what the ampacity lifespan or the fusion time estimate would be. So for 100 amps, it comes out to about 28 milliseconds. And I pulled all the way back to 200 amps, which works out to be just 22 milliseconds. So, if we can get 200 amps, that would give us 4 times the effect that we're looking at for 100 amps. So this chart here, I wanted to see if I use one of the other gauges of wire where I can put more current through without it blowing up, would it be better to go down in gauge to get the higher current rating? Now, if you look here, this is our baseline that we're normalizing everything to. This is our 30 gauge with 100 amps, okay, which we're going to get 28 milliseconds of time out of. This is their effect. The values computed in those previous sections, 1.0 refers to those. So if we want to get twice those effects, okay, for 26 gauge wire, we got up at 218 milliamps through it. Okay, but we can also get twice that effect if we go 30 gauge and put 141 amps in. Going from 100 amps to 141 amps is a lot easier for us technologically than going from 100 amps to 218 amps. So we're going to stick with the 30 gauge wire, and if my estimate is good, we should be able to survive a 10 millisecond pulse with 200 amps to 30 gauge wire. I'd like to see if that's true. Okay, but I don't know if we're going to get there. If we have good results at 100 amps, we're just going to stick with that. Part of the reason why is right now we have the equipment where we can do 100 amp pulses. Okay, we have to order other equipment if we're going to go to 200 amp pulses. So I think our equipment can go up to 123 amps. We could probably do that. Maybe 141 at the asset, but definitely not 200 amps. We're going to talk more about the experiment and the equipment to show you what our limitations are at a later time. Now, again, the experiment we're talking about, measuring the corner current. Okay, now just to clarify something. I've said this is going to be the electrogravitic. Remember the electrogravity paper. The inertial force model is the force of inertia. It's also the force of gravity. So technically, this would be the first experiment in electrogravitics in the history of the world. And that's how we're going to market this, because it is. Okay, so I just want to make that point here. Okay, so the next videos is next week. It's going to be the Venturi charge motion. This is going to be a quick video because it's pretty much just a variation of the centripetal charge motion. After that, we're going to have a long video. Now, this may take me 2 weeks to get to because there's a lot of material here. Or it may break it up into 2 videos. I don't know. The new magnetism V5 models, magnets and wires. And then we're going to have an introduction to the experimental supplements, some of which have already been released. After that, we're going to do the Hall effect video. This is going to be engineering heavy. And then the final version for the new electromagnetism V5 series is going to be the conclusion and the look ahead. For those people that are still on my Distinti YouTube site, please move over to the EtherealMechanics YouTube site. It is EtherealMechanics 5686, or if you put in EtherealMechanics.com, it should take you there. This is the YouTube site that's just got all the version 5 stuff, all the new stuff. The Distinti site, the Distinti YouTube site, has a lot of videos that are 20 years old. And some of them have information that's obsolete. Other information is great. We're holding it there because it basically says we had this idea back then. Okay, but unfortunately I get a lot of comments from people that are talking about old videos that might have something that isn't so great. I don't want to take it down because there's historical stuff going on there. And, you know, hey, this is the Distinti website. This is where you'll find all of the material when it's made public. This is the EtherealMechanics blog site, .info. This is maintained by supporters. Great shout out to Sebastian for maintaining this. Again, when I get more time, when I get through all the experiments and all the stuff, take some more time to visit this site. I apologize for not having a lot of time to spend here. This is the EtherealMechanics Patreon site. If you want to see stuff months, sometimes we produce stuff that's never released to the public. That's all here. If you want to support this, please, by all means, support. No more voodoo physics. Thank you very much.